So now we're going to take a look at these two sample problems of how to calculate the magnetic field. This problem came from the back of the textbook. So we have a strip of current of width W, and the current I is uniformly distributed over the width W. And I'm looking for the magnetic field produced by this strip of current at point P, which is the distance B from the edge, from the closer edge of that strip of current. Now we know how to calculate the magnetic field produced by a very thin, long wire, but this is not a very thin one. It's got a width W. Okay, so what we can do then is to cut this strip into a whole bunch of parallel thin wires and find the magnetic field dB produced by a little thin wire of width dy carrying the current di, and then we get dB. Now all these dBs will have the same direction, which in this case is the B at the point P produced by every part of the current is actually pointing upwards, okay, along the positive z direction. If you cut this strip into a whole bunch of thin wires, each wire produces a dB pointing upwards, so you have to add the magnitude of all these dBs up. So you look at this diagram here, this red line here represents one of those infinitesimally small, thin part of the current. Okay, it's located, this is Y from the center of the strip, point O. And it carries a current DI, which is the total current I times a fraction of dy over W. W is the width of the entire strip. And dB produced by this strip at point P is then mu naught di over 2 pi r, as you get from the Ampere's law. Okay, this is a classic example of Ampere's law. If you were to draw an Amperian loop, which assumes the shape of a circle surrounding the current, which passes through the center of that circle, then you get B dot ds equals 2 pi rb, which equals mu naught I according to Ampere's law. So you get B equals mu naught I over 2 pi r. But in our case, I is to be replaced with di, and r is from that strip to the point P, and that is, we call it r. R equals the total distance from O to P minus y, right? Minus y. Okay, from O to P, we have the distance of half of W from here to there, plus another distance, which is B. Okay, so that's why R equals W over 2, which is from here to there, plus B, and then minus this little segment Y. All right, you plug everything in, and then you get the integral of dB again. You still have to add the magnitudes up because all these dBs have the same direction, right? So all you need to do then is to finish this integral, which will give you a natural log function. And you can finish this calculation yourself, and you can check for the special case when W approaches 0, and then this white strip of current then becomes a thin, long wire, and that reduces the result to mu naught I over 2 pi b. That's the way it should be. You can check that for yourself. Okay, so please finish the integration and check that special case. Now, the second example is when you have a slab of current. Now, we talked about how to calculate the magnetic field of a very large sheet of current with 0 thickness, right? And imagine if this sheet is turned into a slab of finite thickness H, okay? H is the thickness of this slab, and there is a uniform current J, current density J flowing through the cross section. Now this J is the usual definition of current density, which is current over cross-sectional area. It is not the same as the current density defined for the magnetic field of a thin sheet, because that has 0 thickness, so the usual current density would be infinity because thickness is 0. So over there, J was defined to be the current per unit length. Here we define it as normal, the current per unit cross-section area. Okay, given that, what is the magnetic field in space? Let's look at a point, first of all, point outside that slab, say somewhere here. Okay, now because of the symmetry, the B field above this slab of current would be parallel to the slab, and they're all pointing to the left. Okay, they're all pointing to the left. If hold on, pointing to the, no, actually they all point to the right. If you view from this angle, okay, from this angle looking towards the slab, then above the slab, the B field points to the right according to the right-hand rule. Okay, and down the slab, below the slab, they all point to the left, and it has the same magnitude in any plane that's parallel to the slab. Okay, now because of that, we can draw an Amperian loop which assumes the shape of a rectangle like this. From A to B, the B field points directly from A to B, so it's the same orientation as ds, and has the same magnitude. Therefore, the integral between A and B is just B times L. Okay, and then from B to C, the integral is 0 because the direction ds is perpendicular to the direction of the B field, which is parallel to the plane. Okay, you're moving perpendicular to the plane. Same thing can be said from D to A. The integral is also 0. Now from C to D, the field points this way, ds also points this way, and the field is uniform, so it's just again B times L. Okay, B times L. So overall, for the entire loop, the integral is 2BL. And how much is that equal to according to Ampere's law? It is equal to mu naught times the total current enclosed. And so you enclose this much current. How much is that? That would be the current density J times the area enclosed. The area is H times L. Okay, H times L. So H times L here. The two L's cancel on both sides. That is essential. You cannot have an L at the end in the expression for B, because L is simply how long that portion of the loop is. That has nothing to do with the B field. It's just how we solve for the B field. Okay, so there's no L here. It's mu naught JH over 2. And the reason why you have an actual H is only because our J is defined as the normal current density, not current per unit length. You notice that this answer has nothing to do with distance from that point to the slab. You can increase or decrease that distance, you get the same field. Okay. What if you go inside that slab? You look at a point, say here. Okay, the slab is between this line and that line. So you're looking at this point, somewhere inside the slab. What is the B field there? Well, even inside the slab, the B field satisfies the same symmetry, and that is it's got to be parallel to the to the slab. And because of the symmetry, if we find a plane which is in the middle of the slab, then everywhere above that plane, the B field should be pointing to the right. Anywhere below, it should be pointing to the left. And right on that middle plane, the B field should be 0 by symmetry. Okay, so if I want to know the B field at this point, say a distance, let's call it distance y above the middle point, the middle plane, then I can again draw a rectangle like this. Now I can deliberately choose this distance and that distance to be both equal to y, so that I can make sure from symmetry that the strength of the B field here and the strength of the B field there are equal to each other. Okay, so the integral, loop integral from here to there is B times L. This is 0, this is B times L, and that's 0, just following the same argument as here. Okay, so again, it's 2BL, right? The integral is 2BL. And how much is that equal to according to Ampere's law? It is equal to mu naught times the current enclosed. So that's the current enclosed. Again, that will be the area of this loop times J. Okay, the area of the loop is L times 2y, because from here to there is 2y, right? So that gives you the expression for B inside. And you notice that this expression, that expression, they're really the same, except you replace H, the constant H, with a variable y. Okay, that's all the difference there is. And that's inside the slab between y equal to 0 and y equal to what? This point. That's half of L. Okay, I'm sorry, half of H. From here to there, half of H. From here to there, again, the thickness is half of H. Overall thickness is H. So that's what happens when I plot B as a function of y? Okay, y is again the distance to the center, to the central plane of the slab. Within the slab, the B field is a linear function, y, like linear function here. And it turns into a flat line once you are outside that plane. So once you're outside, as you move away from the slab, the B field doesn't change anymore. Okay, constant here and constant here. And you also notice that at the edge of the slab, either here or there, that's where that's why y equals half of h. Okay, half of h. You get the same answer. There is no gap. There's no gap here and here, and that's important to know, because what that means is that there is not a sudden jump in a B field. Now the B field cannot jump suddenly. Okay, the B field cannot jump suddenly, and the reason why it cannot jump suddenly is because the only time B can jump suddenly is when you cross a two-dimensional sheet of current. Just when you cross a two-dimensional sheet of charge, you'll find that the electric field jumps. Okay. Here, this slab, there is no sheet of charge because you didn't press the slab into an infinitely thin sheet. Rather, it's a finite thickness. So there is no two-dimensional charge current distribution. So therefore, the B field cannot change abruptly. Okay. Also, I actually had an extra 2 here. This 2 shouldn't be here because you have a 2 here, you have a 2 here that cancel out. So B inside is just mu naught J times Y. There is no 2 here. And when Y equals H over 2, then you're here. Then you revert to that. Okay, so please cross that 2 out here. All right, so this basically is an exercise on how to apply Ampere's law when you have planar symmetry, and that applies when this plane has finite thickness.